Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Kepler's Cosmic Symphony. Unraveling the laws of the universe. Johannes Kepler stands as one of the most influential figures in the history of science, a man whose work bridged the gap between the mysticism of the Renaissance and the empirical rigor of the scientific revolution. Born on December 27, 1571, in Wilderstadt in the Holy Roman Empire, Kepler's contributions to astronomy and mathematics forever transformed humanity's understanding of the cosmos. His dedication to uncovering the laws governing planetary motion not only solidified the heliocentric model of the solar system but also laid the groundwork for modern physics and celestial mechanics. Kepler's early life was marked by adversity, which shaped his character and his relentless pursuit of knowledge. Born into a modest family, his father was a mercenary who often left the family for long periods, and his mother was an herbalist whose eccentricity brought both fascination and controversy. Despite these challenges, Kepler's intellectual gifts were evident from an early age. He gained a scholarship to study at the University of Tübingen, where he was introduced to the works of Nicholas Copernicus. Under the mentorship of Michael Maestlin, one of the early advocates of the heliocentric model, Kepler became convinced of the validity of Copernicus's theory, setting him on a lifelong quest to understand the intricacies of planetary motion. Kepler's career began in an era when astronomy was still deeply intertwined with astrology and mysticism. As a young man, he was drawn to the idea that the heavens operated according to divine harmony, a concept deeply rooted in Pythagorean and Platonic traditions. In 1596, Kepler published his first major work, Mysterium Cosmographicum, the Cosmic Mystery, in which he proposed that the distances between the planets could be explained by the geometric arrangement of the 5 Platonic solids. Although this model would later be proven incorrect, it demonstrated Kepler's belief in an underlying mathematical order to the universe, a conviction that would guide his subsequent discoveries. In 1600, Kepler's life took a decisive turn when he joined the court of the renowned Danish astronomer Tycho Brahe in Prague. Tycho, known for his unparalleled observational data, became both a mentor and a rival to Kepler. Although Tycho guarded his data closely, Kepler's keen analytical skills eventually gained him access to the detailed measurements of planetary positions. When Tycho died in 1601, Kepler succeeded him as imperial mathematician to Emperor Rudolf II, a position that gave him the resources to embark on his most significant scientific endeavors. Kepler's most enduring legacy lies in his 3 laws of planetary motion, which he formulated between 1609 and 1619. These laws not only described the motions of the planets with unprecedented accuracy but also represented a fundamental shift in the way celestial phenomena were understood. At the time, the prevailing astronomical models, including the Copernican system, still relied on circular orbits and epicycles to explain planetary paths. Kepler's genius lay in recognizing that the planets' orbits were not perfect circles but ellipses. The first of Kepler's laws, known as the law of ellipses, states that planets move in elliptical orbits with the Sun at one focus. This insight, published in his groundbreaking work Astronomia Nova, New Astronomy, in 1609, shattered the ancient Aristotelian and Ptolemaic notions of celestial perfection. Kepler arrived at this conclusion by studying the orbit of Mars, which had long puzzled astronomers due to its apparent irregularities. By meticulously analyzing Tycho's data, Kepler demonstrated that an elliptical orbit accounted for Mars's motion far more accurately than a circular one. This revelation redefined the structure of the solar system, placing the Sun at the center of an intricate, dynamic arrangement of planets. Kepler's second law, often referred to as the law of equal areas, describes the relationship between a planet's speed and its position in its orbit. According to this law, a line drawn from the planet to the Sun sweeps out equal areas in equal times. This means that planets move faster when they are closer to the Sun and slower when they are farther away. Kepler published this law alongside the first in Astronomia Nova, providing a more complete picture of planetary dynamics. The law of equal areas introduced the concept of variability into celestial motion, replacing the uniform circular motion of earlier models with a more nuanced understanding of gravitational influences. Kepler's third law, the harmonic law, emerged a decade later in 1619 with the publication of his work Harmonics Mundi, The Harmony of the World. This law establishes a mathematical relationship between the time it takes a planet to complete one orbit, its orbital period, and its average distance from the Sun. Specifically, the square of a planet's orbital period is proportional to the cube of its semi-major axis. This law revealed a universal order governing planetary motion, uniting the celestial bodies in a harmonious, predictable system. Kepler's laws were revolutionary not only because they provided a more accurate description of planetary motion but also because they emphasized the predictive power of mathematics in understanding the natural world. His work laid the foundation for Isaac Newton's theory of universal gravitation, which would later explain the forces underlying Kepler's observations. Kepler's use of empirical data to derive mathematical laws marked a turning point in the scientific method, demonstrating the importance of observation and measurement in the pursuit of knowledge. Beyond his scientific achievements, Kepler's life was deeply intertwined with the cultural and political upheavals of his time. The 30 Years' War, religious conflicts, and personal tragedies, including the loss of his wife and several children, cast shadows over his career. Yet, his resilience and unwavering dedication to uncovering the mysteries of the cosmos stand as a testament to the power of human curiosity and determination. As Johannes Kepler continued to unravel the mysteries of planetary motion, his work became increasingly characterized by precision, perseverance, and a relentless drive to integrate mathematics with the observable universe. Having already revolutionized astronomy with his first two laws, Kepler now turned his attention to refining his theories, tackling broader cosmological questions, and addressing the technical challenges of the time. His insights not only deepened humanity's understanding of the cosmos but also underscored the interconnectedness of natural phenomena, uniting celestial mechanics with broader physical principles. Kepler's third law, often referred to as the harmonic law, emerged from his lifelong fascination with harmony and geometry. His earlier works, particularly Mysterium Cosmographicum, reflected his belief that the universe operated on principles of divine proportion and order. While his initial attempts to link planetary distances with geometric solids proved incomplete, they instilled in him a conviction that the motions of celestial bodies adhered to mathematical relationships. By the time he published Harmonics Mundi in 1619, Kepler had refined these ideas into a groundbreaking revelation. The square of a planet's orbital period is proportional to the cube of its semi-major axis. The harmonic law demonstrated that the outer planets, with their greater distances from the Sun, moved more slowly and took longer to complete their orbits than the inner planets. This elegant equation highlighted the interconnected nature of the cosmos and reinforced the heliocentric model proposed by Copernicus. Kepler's third law was also significant because it described a universal relationship, one that applied to all planets without exception, revealing an underlying order to their motion. The third law's implications extended far beyond astronomy. By showing that planetary orbits could be described mathematically, Kepler laid the groundwork for the application of mathematical laws to other areas of physics. This principle of universal applicability would later be expanded by Isaac Newton, who used Kepler's laws as a foundation for his theory of universal gravitation. Newton's work demonstrated that the same force governing the motion of planets also applied to objects on Earth, uniting terrestrial and celestial mechanics in a single framework. Kepler's innovative approach to astronomy extended to his work in optics, where he made significant contributions that advanced both theoretical understanding and practical applications. In 1604, he published Astronomiae Pars Optica, the optical part of astronomy, a treatise that explored the principles of vision, lenses, and the behavior of light. In this work, Kepler described the process by which images are formed on the retina, laying the foundation for modern optics. He also investigated the principles of refraction and reflection, insights that would later prove invaluable in the design of telescopes. Kepler's fascination with the interplay of light and celestial phenomena also led him to study the behavior of comets and the nature of the Milky Way. He proposed that the Milky Way was composed of countless individual stars, a bold assertion for his time that anticipated later discoveries made with more powerful telescopes. His investigations into the geometry of snowflakes and the hexagonal symmetry of their crystals showcased his interdisciplinary curiosity, as he sought to uncover mathematical patterns in natural forms. Kepler's achievements also faced resistance from some of his contemporaries. While the heliocentric model gained increasing acceptance, many astronomers and philosophers clung to traditional views rooted in Aristotelian and Ptolemaic thought. Even among supporters of the Copernican system, Kepler's elliptical orbits and non-uniform planetary speeds represented a departure from the idealized circular motions that had long been considered the hallmark of celestial perfection. Nonetheless, Kepler's meticulous calculations and the predictive accuracy of his models eventually won over skeptics, securing his place as a pivotal figure in the scientific revolution. In the twilight years of Johannes Kepler's life, his commitment to uncovering the mysteries of the universe remained as resolute as ever. Despite the many challenges he faced, political upheaval, personal loss, and persistent financial struggles, Kepler continued to produce work that would cement his legacy as one of the greatest scientific minds in history. His final years were marked by a blend of profound scientific achievements, philosophical reflections, and an enduring quest to reconcile the celestial and the terrestrial. Kepler's crowning achievement, the Rudolphine Tables, published in 1627, represented the culmination of decades of meticulous work. These tables, built upon Tycho Brahe's observational data and Kepler's groundbreaking laws of planetary motion, provided the most accurate predictions of planetary positions and eclipses of the time. The Rudolphine Tables were not merely a practical tool for astronomers and navigators. They were a testament to the power of mathematics and empirical data in deciphering the cosmos. For centuries, these tables served as a cornerstone of celestial navigation and astronomical research, influencing the course of exploration and scientific inquiry. Kepler's ability to derive universal principles from empirical observations reflected his unique approach to science. He viewed the natural world as a harmonious system governed by mathematical laws, a perspective rooted in his belief in a divine order. This synthesis of science and spirituality was evident in his final major work, Somnium, the Dream, published posthumously in 1634. Often regarded as one of the earliest works of science fiction, Somnium explored the idea of space travel, imagining a voyage to the moon and speculating on the celestial mechanics that would make such a journey possible. Through its narrative, Somnium also illustrated Kepler's deep understanding of astronomy, describing the motions of the Earth and Moon with remarkable accuracy for its time. In addition to his scientific contributions, Kepler's philosophical musings in Somnium and other writings reveal his enduring fascination with humanity's place in the cosmos. He grappled with questions that extended beyond the physical realm, contemplating the relationship between nature, mathematics, and the divine. Kepler's belief in the interconnectedness of all things inspired him to seek patterns and principles that unified the seemingly disparate phenomena of the universe. This holistic vision of science, which sought to bridge the gap between empirical observation and metaphysical inquiry, set Kepler apart from many of his contemporaries. Kepler's life was not without its struggles. His unorthodox views often placed him at odds with the religious authorities of his time. Despite his Lutheran faith, Kepler's efforts to reconcile religious doctrines with scientific discoveries frequently brought him into conflict with both Protestant and Catholic factions. His refusal to fully align with dogmatic interpretations of Scripture and his support for Copernican heliocentrism made him a controversial figure. Nevertheless, Kepler remained steadfast in his pursuit of truth, guided by his conviction that the study of the heavens revealed the majesty of creation. As Kepler's health began to decline in his later years, he found himself increasingly burdened by financial difficulties and the instability of the Holy Roman Empire. The 30 Years' War disrupted his work, forcing him to relocate multiple times and diminishing the support he received from imperial patrons. Despite these hardships, Kepler's final years were marked by a sense of fulfillment and purpose. He continued to correspond with leading scientists and thinkers of his era, sharing his insights and advocating for the importance of empirical observation and mathematical reasoning. Kepler passed away on November 15, 1630, in Regensburg, Germany, leaving behind a legacy that would shape the course of science for centuries to come. His revolutionary laws of planetary motion not only transformed astronomy but also laid the foundation for the development of classical physics. Isaac Newton's formulation of the law of universal gravitation, which provided the theoretical framework for Kepler's empirical observations, stands as a testament to the enduring impact of Kepler's work. Beyond his contributions to science, Kepler's legacy endures in the broader cultural and intellectual landscape. His ability to merge empirical rigor with philosophical inquiry exemplifies the spirit of the scientific revolution, a period that redefined humanity's understanding of the universe and its place within it. Kepler's writings continue to inspire scientists, philosophers, and artists, reminding us of the power of curiosity, creativity, and determination in the pursuit of knowledge. As we reflect on Johannes Kepler's extraordinary life and achievements, it becomes clear that his work was not merely about understanding the motion of planets or the nature of celestial bodies. Kepler's discoveries revealed a universe governed by order and harmony, a cosmos where the interplay of mathematics and nature offered profound insights into the workings of the divine. His contributions serve as a bridge between the mystical traditions of the Renaissance and the empirical methodologies of modern science, embodying a timeless quest to uncover the secrets of the stars. In celebrating the life of Johannes Kepler, we honor a visionary whose insights have illuminated the heavens and deepened our appreciation of the universe's beauty and complexity. His legacy reminds us that the pursuit of knowledge is a journey without end, one that continues to inspire and challenge us to reach for the stars.